Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com.
Hello, everyone.
Today we are starting a very important topic from Unit 2, electrostatic potential and capacitance.
And the topic is the parallel plate capacitor.
Yes. Now, I know many students getting confused here, but we will make it simple and completely exam safe.
I hope so.
Yeah.
This chapter always feels a bit abstract to me. Just lines and formulas. It's hard to really picture it.
We will fix that picture today. But before we even touch the textbook, let me ask you one thing.
Okay.
When you are typing on your computer keyboard, how does the computer know you pressed a key? You are just pushing a plastic button? No.
I never really thought of that. I thought it's just touching a wire or something, like a doorbell switch.
That's a good guess. But not just touching wire. Actually, inside the keyboard, under the key, you are changing the physics.
The physics.
You are changing the capacitance.
Wait, what? So when I'm typing, I'm doing something with capacitors.
Exactly. Actually, some keyboards work by changing the distance between two small plates. When you press, the distance becomes less.
Okay.
This changes the capacity, a signal goes, and the computer knows you pressed A. This is the magic of the parallel plate capacitor.
That's actually really cool. It's not about touching. It's about getting closer.
Precisely. And that's our topic. So what is this parallel plate capacitor? Very simple.
Okay. From the basics.
Take two metal sheets. Put them parallel to each other.
Right.
Do not touch them. Keep a small gap.
A gap in between.
Connect it to a battery. One plate becomes positive, one becomes negative. They want to touch, but the gap is there, this tension. It stores energy.
So they're attracting each other but can't reach.
Yes. Think of a bread sandwich.
A sandwich.
Yes. The two slices of bread are your metal plates.
Okay, bread slices are the plates.
And the filling in the middle, the cheese or whatever, that's the gap. That's the electric field.
So the filling is the field.
Now, if the filling is very thin, meaning the distance is small, the sandwich holds together very strong, correct?
Yeah, the attraction is strong.
The flavor or electric field is strong. If the filling is thick, the interaction is weak.
So a small distance is better for a capacitor.
Exactly. Or, here's another mental image. Imagine two dance floors facing each other.
Okay.
The ceiling is the positive plate. The floor is the negative plate.
Right.
And in between, there are straight pillars connecting top to bottom. These pillars are the electric field lines.
Ah, so they are uniform and straight.
Perfectly straight, yes. So the plates are just holding the charge, like a bucket.
Yes, that's what I was thinking. They're like containers for charge.
Correct. But here, the capacity of the bucket depends on how close the plates are. Closer is better.
That makes sense.
Now, let us see how NSERT defines this formula. Read the formula for the capacitance of a parallel plate capacitor.
Okay, let me find it. It says C equals epsilon naught A divided by D.
Good. G $, is area of A. What is this epsilon naught A by D? Let's break it down.
Okay.
See, A is area. A is on top in the numerator.
Right.
Meaning, if area is big, capacitance is big, more space on the dance floor, more people can dance. It's a direct relation.
So bigger plates hold more charge.
Simple. But D is distance. D is down in the denominator.
Which means it's an inverse relation.
And what does that mean?
If the distance is more, the capacity is less. Like magnets, if they're far away, the pull is weak.
Perfect. So, to make a good capacitor, make area big, make distance small.
Big area, small distance. Got it.
Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com.
Okay, so A and D make sense. But what about that epsilon naught, the epsilon dollar?
Yes. It's just a constant in nature. Think of it as the permission that empty space gives for an electric field to exist. It just makes the units work out.
So it's like a fundamental rule of the universe for electric fields.
You can think of it that way, yes. Now, one small twist. What if we put something inside the sandwich? Not air, but say plastic or glass.
That is a dielectric, right?
Yes. Think of a sponge in a water bucket.
A sponge.
If you put a sponge in the bucket, it soaks up water. So now you can pour more water to reach the same level, correct?
Right, the sponge holds some of the water.
Same way, a dielectric soaks the field so you can store more charge at the same voltage.
So the dielectric helps you store more. How does that change the formula?
The formula changes slightly. C becomes K times C. So it's C to dollar, frec epsilon A to D.
And this K is the dielectric constant.
Yes, and K is always greater than 1. So a dielectric always increases capacity.
Always. Okay.
Let's do one oral calculation. Very important for the exam.
I'm ready.
Suppose I have a capacitor. I double the area, so it becomes $2.11, and I make the distance half, so $2.02. What happens to the new capacitance?
Okay. Area is double,
Yeah.
so that's a times 2, and distance is half.
Yes. Think step by step. Area is on top, so you multiply by 2.
Okay, a factor of 2
And distance is down. Dividing by half means.
multiplying by 2 again.
So the total is?
2 into 2 equals 4. The capacitance becomes 4 times.
Absolutely correct. It becomes 4 times bigger. Simple? No.
Yes, that's a straightforward mark if you just apply the formula.
By the way, this whole concept connects back to Unit 1. Remember we did field of an infinite plane sheet?
Oh, right. Using Gauss's law.
This is just 2 of those infinite planes put together, one positive, one negative.
So the concepts are linked.
They are always linked. Now, be careful. 2 places where students lose marks. The silent killers.
Oh, okay, what are they?
First misconception. The field outside the plates. Many students think the plates have charge, so there must be an electric field outside also.
Well, yeah, I would think so. A positive plate should create a field around it.
Wrong. For an ideal capacitor, outside the plates, the positive field and the negative field cancel each other out.
They cancel.
Because the field from one large sheet is uniform, it doesn't depend on distance. So the push from the positive plate and the pull from the negative plate are equal and opposite. They cancel. E is practically 0.
Wow, okay, so all the action is between the sheets.
Exactly.
So just to be clear, outside it is 0 and inside it is uniform.
Correct. Inside uniform, outside 0. Remember that.
Got it. What's the second mistake?
Second mistake. Students think inserting a dielectric increases the voltage.
It doesn't.
No. Remember this phrase, dielectrics die the field.
Die the field.
Yes. It acts like a damper. It reduces the electric field, which reduces the potential, V, if the charge is isolated.
So it lowers the voltage.
Or if it's connected to a battery, it pulls more charge to keep the voltage the same. It does not increase voltage on its own.
Right. That goes back to the connected versus disconnected case we talked about.
Exactly. So let's create some memory anchors. How to remember the formula.
Right.
Remember the phrase A over D, it sounds like aid. Capacitance aids storage. So A is up, D is down. Yeah.
A over D.
Aid. That's a good one.
Now do this with your hands. Keep your hands parallel like plates.
Okay, like this.
Bring them close, strong force, C goes up. Pull them far, weak force, C goes down. Capacity is geometry.
Closer is stronger. Makes sense.
And for the dielectric, remember, K is king.
K is king.
K always makes the capacitance bigger. Always. It's the king multiplier.
Okay, these are really helpful. Aid, K is king, and the hand gesture.
So 3 points to put in your pocket for the exam. Ready?
Yes. 1,
the formula is d-element fraxel NOD, area on top, distance down.
Right.
2, inside the plates, the field is uniform. Outside the plates, the field is 0.
Inside uniform, outside 0. Check.
And 3, if you insert a dielectric with constant K, the capacitance increases K times.
C becomes K times C. Got it.
Excellent. This is much clearer now, right? The physical meaning behind it all.
Yes, much better. The sandwich and the sponge analogies really help visualize it. It's not just a formula anymore. That is the goal. Physics is never just formulas. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
Thank you.
Keep practicing. But before we go, one final thought for you to think about.
Ooh, what is it?
We said for high capacity, you need a big area, like a football field of area.
Right.
But you cannot fit a football field inside your mobile phone.
No, definitely not.
Yet, your phone has tiny capacitors with huge effective areas. How do they do it?
I have no idea. How is that possible?
Think about the shape. What if the plates were not stiff metal sheets? What if they were thin foils, like aluminum foil, and we rolled them up?
Rolled them up like a chapati or a Swiss roll.
Exactly like a Swiss roll. You put a thin sheet of dielectric in between, and you roll it all up into a tiny cylinder.
Oh. So you get a massive surface area, but in a very small volume.
I get the massive area, but the volume becomes tiny. That is why almost every capacitor you see in a circuit looks like a small can. It's a geometry hack.
That's brilliant. So it's still parallel plates. They're just rolled up.
Exactly. Think about that. We'll see you in the next deep dive.